Hello everyone, welcome to the presentation of our paper on the projection operator to a three-view cardinality constraint set. In many real problems, the cardinality of the sparsity restriction is an intrinsic requirement. For example, shopping websites like Amazon need to recommend a list of items online. There are many categories of goods such as book, computer, sports equipment, clothing, and many others. To maximize the combo effect, empirical experience suggests that the diversity in recommendation can significantly increase the click rate. So it is a natural idea to ensure a certain diversity when we design the recommendation list. The next example is the task worker assignment in crowdsourcing. In this problem, we use a binary matrix to indicate the assignment. 1 means the task is assigned to the worker, and vice versa. For example, we have 5 images to be labeled by human. Each row of this matrix corresponds to a worker, and each column corresponds to an image. With the cardinality restriction, we can guarantee that our assignment solution will not assign more than 2 images to a worker. In addition, no more than 2 workers to the same image. The third example is a gene network identification. As the left figure shows, gene network is a directed graph, and most nodes only connect to a small number of other nodes, which means that it is a sparse graph. We use the adjacent matrix to represent the directed graph. 0 means that these 2 genes, or nodes, are not connected, and a non-zero value indicates how these 2 genes are correlated. The row-wise and column-wise cardinality constraints can restrict the out degree and in degree for all nodes. Now let's use a unified optimization framework to summarize all these examples. The objective function is over a vector W, and the constraints are encoded by the set omega, which is the cardinality restriction of W in terms of several predefined groups. We use L0 norm to denote the cardinality, which is the number of non-zero elements in the argument. Here we have several predefined groups. Each of them is an index set, and big G is a hyperset which is a collection of all those groups. Of course, different predefined groups will give a totally different constraint set here. For a special case, if we only have one group covering all the coordinates of W, we have exactly the same constraint as a standard sparsity constraint. These 3 motivating examples can be summarized into a 3-view cardinality structure. We call it TVCS in short. In this structure, we can have groups coming from 3 different hypersets, including a set G0 with all variables. Groups in the same hyperset cannot overlap with each other, but there is no such requirement for groups from different hypersets. We can see that the definition basically gives some rules about how the groups can overlap. We will see that the examples mentioned before totally admit such TVCS definition. Here we provide 2 common examples satisfying the TVCS structure. Example A includes 8 groups in total. In the online recommendation case, except group 0, each group indicates a category. We need to restrict the maximum number of items selected from each group to maintain the diversity. Example B shows how our structure can be used to control the cardinality within each row and column. In addition, cardinality over all the coordinates can be restricted at the same time. By this way, it covers the gene network identification and task worker assignment problems. This generic optimization is very hard to solve directly. The commonly used approaches, including IHT and COSAM, both requires the k-step projection. The projection operator returns the nearest point in the constraint set omega. Although the projection problem seems much easier than our original problem, it is still non-trivial because there exist overlaps among groups. It is NP hard if there is no regulation for the groups. In this work, we solve the projection problem with TVCS in the following steps. Firstly, we formulate it as equivalent integer linear programming. The objective function is a linear function. Besides the linear inequalities, we have the integer constraints, which makes this problem discrete. Here matrix A encodes all the predefined groups. For example, if A is a 2x3 matrix like this, it means we have two groups, and each with indices corresponding to the non-zero positions in the rows of A. The variable x is a binary vector. The non-zero element in optimal x indicates that the corresponding element in optimal W is selected, or non-zero. If we know that the S element of optimal W is non-zero, its optimal value should be just Vi. Next, let's just relax the integer constraints to the box constraints. Obviously, it becomes a linear programming. Both the objective function and the constraints are linear. Although linear programming is what we like, we should be very careful since the solution to the linear programming is not necessarily integer, and simply doing rounding may disobey the linear inequalities. Fortunately, we have a theory which guarantees that for any group following our TVCS definition, the relaxed linear programming has integer optimal solution. In addition, all the vertices of its feasible set are integer points. Simplex method can guarantee to find a solution in the vertex of a polyhedron. But it could be very inefficient in some extreme cases and lack rigorous theoretical guarantee for complexity. Here we present an efficient algorithm. Firstly, let's write the dual problem for the original linear programming. Here y is our dual variable, and of course this is also a linear programming. Using the fact that the duality gap of linear programming is 0 when we reach the optimal point, we can reformulate the linear programming as a feasibility problem. Then we only need to handle the linear constraints. Next, we further rewrite the feasibility problem into an optimization problem with a quadratic objective function and simple box constraints. This problem is a convex problem and it meets the optimally strongly convexity. So it can be shown that the projected gradient descent method ensures a linear convergence rate on this problem. The matrix A encoding linear inequalities from our TVCS model is actually sparse, which leads to a linear time complexity to calculate the gradient of such objective function. In addition, since we know the optimal solution is integer, so we can round the solution when it's sufficiently close to the true solution. Therefore, the total time complexity for this method is in the order of the number of variables, plus the number of groups, and times the number of iterations we need, which is the logarithm term. In the experiment part, firstly, we validate our method using linear regression and classification on the synthetic data. We generate the ground truth as the matrix case mentioned before. The compared methods, including only restricting the row-wise or column-wise sparsity and only restricting the overall sparsity. In addition, we also compare with exclusive lasso in the linear regression task. Here are the figures of the result. We evaluate the feature selection recall, the recovery rate, the classification error in terms of different numbers of samples provided. In linear regression, our method has the best feature selection recall for all the choices of sample size, although exclusive lasso have similar feature selection recall when the number size is small. In the classification task, we use the squared hinge loss and the L2 regularization for both the feature selection recall and the classification error. We can see that our method outperforms others with a significant margin. We applied our method in the cross-sourcing task assignment. In the experiment, we assign M tasks to N workers and gradually increase the assignment number. We apply the cardinality constraints in maximizing the expected accuracy. The compared methods including random assignment and greedy assignment based on the quality matrix, which we call it Q-based method here. The figures show that the expected accuracy of the crowdsourcing task. We can see that the directly maximizing the expected accuracy will be slightly better than the Q-based method, and both of them are much better than random assignment. And last, we evaluate our methods in gene network identification. We collect the gene expression at different time points and use their difference to estimate the correlation of different gene nodes. The estimation is formulated as an optimization problem with the TVCS constraints. This table shows that for the accuracy, F measure, and the AUC score, our approach outperforms several other gene identification methods. Okay, in conclusion, we introduce a sparsity structure TVCS and propose an efficient projection operator for it. We apply the proposed TVCS model in several real problems and validate its effectiveness via different experiments. In the future, we'd like to improve its flexibility and explore more applications. Here are some references. Thank you.